Hi, my name is Staci Smith, and today I'll be talking about work I did at the University of Arizona as a graduate student with my PhD advisor, Dave Lowenthal. So this work is on a new scheduler called Jigsaw, which is a high utilization, interference-free scheduler for fat tree clusters. And when I say interference-free, I mean free of network interference. So first of all, why do we need an interference-free scheduler for HPC systems? So on most HPC systems today, the job scheduler allocates dedicated nodes to jobs for performance reasons, so that each job has isolated compute resources, such as memory, on its node. However, most schedulers do not treat the network as a dedicated resource, so all the jobs on the system share the network and compete for bandwidth. For example, on the right here is an image of a system with a 3D torus topology, and the different colors represent different jobs running on the system. As you can see, there's a bright blue job there at the bottom, and it's surrounded by a green job with many nodes. So you can imagine when the green job communicates across the network, a lot of its messages will travel across the same network links that the blue job is using and create inter-job network interference. Now, in this work that this image comes from, and in plenty of subsequent research, we've seen that this inter-job network interference can lead to significant performance degradation for jobs, and hence significant performance variability. So we need some solutions to mitigate the effects of inter-job interference. Now, our work is focused on systems with a fat tree network topology. So I need to briefly explain the fat tree topology and define the terminology that I'll be using in the talk. As you can see here in this example, a fat tree topology is a tree-like topology with different levels of switches. So the bottom level of switches are called the leaf switches, and all of the nodes in the system are connected to the leaf switches. Above that are L2 switches, and above those are L3 switches. And the top level of switches in a fat tree are also called the spines. You can see each switch has connections to multiple parents as well as multiple children. And in our work, we're looking exclusively at full bandwidth fat trees, which means that each switch has the same number of connections to parents as connections to children. In practical terms, this means that the total bandwidth across the machine doesn't get tapered as you go up the fat tree, but it's constant. And a related property is that full bandwidth fat trees are rearrangeable non-blocking, which I described the definition of in the paper. But for the purposes of this talk, whenever I say full interconnect bandwidth or full bandwidth, what I mean is that a partition is rearrangeable non-blocking. Finally, our work focuses on three-level fat trees, like this example. And you can see that a three-level fat tree contains multiple two-level fat trees connected together by the spine switches. And I call each of these two-level fat trees a subtree in this talk and in the paper. So with those preliminaries out of the way, I can briefly describe the possible approaches to mitigating network interference. One approach is to schedule jobs as usual on any nodes that are available, and then to implement routing policies to try to dynamically route around congestion in the network at runtime. And this can help to alleviate inter-job network interference when it's successful. The second approach is to actually change the scheduling policy so that it guarantees isolated network partitions to each job. For example, you can accomplish this by allocating network links as a dedicated resource, the same way you currently allocate nodes as a dedicated resource. The major shortcoming to date of such schedulers is that they tend to lower system utilization. Because the scheduler becomes more constrained, it can't always place a job even when nodes are available to it. So the node utilization in the system is typically lower than with a regular scheduler. However, there's a major advantage to using the scheduling approach because it completely eliminates outside network interference for jobs, which the routing approach can never do. So in our work, we have developed a new interference-free scheduler for fat trees, which has higher utilization than previous work. It accomplishes utilization within about 5% of baseline scheduling, which is high enough to allow adoption on current systems. So now I'll get into the details of our work. So when we set out to design the scheduler, there are 3 goals that the scheduler needs to accomplish. The first, obviously, is that it needs to provide network isolation to jobs, and this is a hard constraint. The second is that it needs to continue to provide full interconnect bandwidth to each job, which is also a hard constraint. And I'll talk a lot more about the full interconnect bandwidth in a minute, but to give the intuition behind this, you don't want to allocate a partition to a job that has significantly less bandwidth than the underlying fat tree topology does, because then the performance of the job may suffer from intra-job congestion. Finally, a major goal of our work was to achieve the highest utilization possible. And while there's no hard constraint on the utilization we achieve, we need to get as close to baseline as we can to encourage adoption of the scheduler. It turns out that satisfying all 3 of these goals at the same time is very difficult, and our work does this. Now currently, there are 2 state-of-the-art approaches to interference-free scheduling on fat trees. One called topology-aware scheduling, or TA, and another called links as a service, or LAS. Now, both of these achieve 2 of the goals for our scheduler. They both provide network isolation and full interconnect bandwidth for the jobs. But they're actually overly constrained in their placements, so they end up suffering from system fragmentation, and the overall system utilization is about 10% lower than baseline, or more, for both of these. Unfortunately, I don't have time to go into the details of these 2 approaches during the talk, but there are lots of details in the paper and an in-depth comparison of our work versus the state-of-the-art work. And in this talk, I will use these as points of comparison for our performance since they're state-of-the-art. So basically, the key to our work is to try to reduce fragmentation so that we can increase utilization while still maintaining isolation and full bandwidth. Basically, we need to avoid being overly constrained in our placements in order to help reduce fragmentation. So the basic approach with Jigsaw is that we allocate dedicated links to each job to provide isolation, and at the same time we carefully select nodes and links for each job to provide full bandwidth. And this is the difficult part of the work, figuring out how to select nodes and links to provide full bandwidth without being overly constrained. And this is what we provide that previous work did not. So why is it hard to find nodes and links to give out? I'd just like to go through a few examples of what can go wrong with different node link combinations in terms of bandwidth. So in this first example, this is a 3-level fat tree, and the job is a 4-node job that has been allocated the nodes and links that are highlighted in blue with dashed blue lines. In this case, it's only been allocated 2 links between the L2 switches and the spines, so a single spine to connect the 2 subtrees. And what happens in this case is if the 2 nodes on the right try to send messages simultaneously to the 2 nodes on the left, the 2 messages will be forced to share links at the top level. Basically, this is a tapering of the partition, and this violates the full bandwidth. So the takeaway from this is that just as the underlying full bandwidth fat tree has the same number of connections to parents and children at each switch, our partitions also need to have the same number of connections to parents and children. So in this second example, we have rectified that error, that each of these leaf switches now has the same number of connections to parents as it has nodes attached to it. However, we have distributed the nodes arbitrarily across the leaves. And by that I mean we have 3 nodes on the first leaf, 2 on the second, and 1 on the last leaf. And it turns out that if the 3 nodes on the right try to send messages to the 3 nodes on the left, they are still forced to have 2 of the messages go over a common link. In this case, the leftmost link in the allocation. And this is because of the arbitrary node placement. So we see that node placement can also have an effect on the bandwidth of the partition. Finally, we have to be careful in how we select the L2 switches and the spines to connect to. So in this example, at each L2 switch, I have independently picked a different spine to connect to without considering where the other L2 switches are connecting. And if the two nodes on the left try to send messages to the two nodes on the right, and you distribute those two messages across different paths that are available, one of the messages ends up reaching a spine that can't get to the receivers. So because we have not carefully selected which L2 switches and spines to connect to, there's still a lack of connectivity and the full bandwidth is violated. With all those in mind, we have developed a set of constraints for node and link allocation, which turns out to be the minimal constraints required to provide full bandwidth in a partition. And here I'll just describe the constraints along with a running example of placing an 11-node job onto this fat tree following these constraints. So first of all, the nodes must be evenly distributed across subtrees, except for possibly the last subtree, because the nodes may not evenly divide into the number of subtrees. In this example, there are 4 nodes per tree, except for the last tree, which has only 3 nodes, and we call that last tree the remainder subtree. Similarly, within a subtree, the nodes must be evenly distributed across the leaves, except again for the last leaf. So here, every leaf in the allocation has 2 nodes assigned to it, except for the last leaf, which has only 1 node, and we call that the remainder leaf. Now the next set of constraints have to do with how we select links or switches to connect to. So within a subtree, the leaves that have nodes allocated must connect to a common set of L2 switches. Here both leaves have to connect to the same first 2 switches in that subtree. Then across subtrees, every subtree actually has to connect to the same set of L2 switches as the other subtrees. So in this example, you can see since the first tree had connections to the first 2 L2 switches within that tree, the other trees must also use the first 2 L2 switches within the tree. Finally, there's a similar constraint to selecting spines to connect to. So each subtree must connect to a common set of spines. Here I show how the first L2 switch in every tree connects to 2 spines that are in common, and then the second L2 switch also connects to 2 spines in common. Once you have all those constraints in place, you have a valid allocation for this 11-node job, and this allocation has full interconnect bandwidth. By that I mean that it is rearrangeable non-blocking, as I mentioned before, and we have proved that the set of constraints is both necessary and sufficient for a partition to be rearrangeable non-blocking, meaning that this is the minimal set of constraints, and a scheduler that leverages these constraints will be the least constrained possible. So, as I mentioned before, having precise constraints that are not overly constrained helps us in reducing fragmentation and achieving higher utilization. But there's actually a second key to our work as well, which is that to further reduce fragmentation, we can try to restrict placements to be as compact as possible. So that leads me to the policy for Jigsaw. Jigsaw, our scheduler, assigns allocations that fit these constraints so that full bandwidth is guaranteed to each job. But it actually assigns only a subset of the possible placements. So when a job has to span 3 levels, has to have an allocation that spans 3 levels, Jigsaw will only give out allocations that use all nodes per leaf. So for example, under the Jigsaw scheduler, the allocation that I just showed right now would actually not be given out because it only uses 2 nodes out of the 3 nodes on each leaf. But this allocation that uses 3 nodes per leaf would be given out by Jigsaw and considered a legal placement. And again, this is to help reduce fragmentation over time so we can achieve a higher utilization. So now that I've described how the Jigsaw scheduler works, I'd like to go over a couple of performance results for it. So in the paper we evaluate on a number of metrics compared to a baseline scheduler, and to the state-of-the-art schedulers, LOS and TA. And here in this talk, I will present results for utilization and also for job turnaround time. So this figure shows the average utilization for different scheduling techniques on a variety of job traces that we evaluated. So the x-axis has the different job traces. The first 3 are synthetic traces that we generated, and the last 6 are job traces from real machines, Atlas, Thunder, and Cab. On the y-axis is the average utilization. The y-axis starts at 80% so that you can clearly see the differences between the different approaches. And obviously a higher utilization is better. So we see the baseline, which are the gray dots, often achieve utilization close to 100%. And then Jigsaw, which are the x's, achieve utilization at or above 95% in most of the cases, and are within about 5% of the utilization of baseline scheduling. The next best competitor is LOS, which is more typically around 90% utilization. And then TA comes in third with between 85 and 90% utilization. So we see here that Jigsaw achieves utilization at about 95 to 96% for most job traces, which is high enough to allow it to be used on a real system. And it also recovers about half of the lost utilization compared to the state-of-the-art techniques existing today. Now, I'd also like to talk a little bit about job turnaround time with each of these approaches, because one consequence of lower utilization is that job wait times and hence job turnaround time can reduce. And job turnaround time is defined as the time between when a job enters the queue and when it completes running. So with lower utilization, you can have a larger turnaround time because fewer nodes are being utilized and fewer jobs can be scheduled. But at the same time, with an interference-free scheduler, you may get a performance boost. You expect to get a performance boost from the lack of network interference. So that can counterbalance the lower utilization. So here we evaluated average job turnaround time for the different techniques with a variety of scenarios with different amounts of performance improvement under interference-free scheduling. The different scenarios are shown on the x-axis. So the first one is the case in which the jobs perform exactly the same under regular scheduling and interference-free scheduling, which is obviously the worst case for an interference-free scheduler. The other 5 scenarios assume different amounts of performance improvement. So, for example, the 10% cluster of bars assumes a 10% performance improvement for jobs when they're run with interference-free scheduling. The y-axis shows the turnaround time normalized to baseline, so values below 1 are good because it means the turnaround time is lower than baseline turnaround time. And values above 1 mean that the turnaround time is worse than baseline turnaround time. Finally, each bar has a filled portion, which is shown with the hatched area, and the full portion. And the hatched area shows the average for all jobs in the trace, whereas the full portion shows the average for large jobs in the trace, because large jobs tend to have to wait longer to be scheduled with interference-free scheduling. We can see, if we look at just the hatched portion of the bars, for each scenario in which there is some performance improvement with interference-free scheduling, Jigsaw always beats baseline, has a lower average turnaround time. And even in the case where jobs have no performance improvement, it is only slightly worse than baseline because the utilization is so close to baseline utilization. Even if we look at the large jobs, Jigsaw still improves the average turnaround time in some scenarios if performance improvement is large enough. And we do better than topology aware and LOS in all of these cases as well because the utilization is higher. So in summary, our work presents a theoretical underpinning for isolated partitions on 3-level fat trees. Specifically, we provide the minimal set of constraints for a partition to have full interconnect bandwidth. The Jigsaw scheduler leverages this to eliminate inter-job interference while obtaining a higher utilization than state-of-the-art schedulers that do the same. So our utilization is around 95%, which is high enough to be considered for adoption on a real system. Finally, because our utilization is so close to baseline, our job turnaround times are actually often better than baseline, provided that jobs perform even slightly better in an interference-free setting than a normal setting. Finally, I'd just like to let you know that all the code for our work is available at this OSF repository. And there's also an extended version of the paper available, which includes the full proof that the constraints are necessary and sufficient for full interconnect bandwidth. So thank you for listening to this talk today, and I look forward to the live Q&A.